Hello, we're going to start our first lecture. We're starting with chapter 11 in the edition of book that you have. And the chapter's title is Solutions and Their Properties. And we're only going to do the first four sections. We just really want to introduce the idea of solution and concentration units and why solutions form. So the way I'm going to do the lectures is I will run through PowerPoint slides for each chapter. And then after I do that, I'll do a second lecture doing a few worked example problems to help you get started on your homework. So then we'll have class in person, at which point you'll be able to ask questions and we'll run through some activities that I hope will even solidify things better. So as you get started, I think you should think that watching the lectures is important. You could also read the chapter instead. It'd be perfect if you could do both, but I don't think on the block plan there's always time for that. So what I would do is I would watch the lectures, then I would try the homework. And if I had big questions on the homework, and if I remembered it from the lecture, I might go back and rewatch that part of the lecture. If I didn't remember it from the lecture, I would probably read that section in the textbook to see if there was something that I didn't talk about that might have been in one of the problems. So I'm going to share the PowerPoints. Okay. Okay, so these PowerPoints are from a newer edition of the text, which we've used in past years. So their chapter numbers will be different, but this is exactly what's in chapter 11, the first four sections. So solutions and their properties. So a solution is a homogeneous mixture. So things are mixed, you don't have particles separate of the liquid, or if it's two solids, they're completely mixed in a homogeneous way. The solvent, because you can have liquids, gases, and solids, the solvent is usually defined as the major component, so that's present in the largest excess, and the solute is the minor component. So this table, which is also in your text, just shows you some of the kinds of solutions you might be familiar with. Gas and gas, which is the air we breathe. There are lots of different gases in there. The solvent in that case would be nitrogen, and the others would all be solutes. So nitrogen is the primary component of air. The primary one we're going to think about are liquid and solid, and solid and liquid and liquid, and liquid and solid. So we'll talk a lot about these kinds of solutions. Almost all of the work we do in this class, the solvent will be water. We'll be talking about things that are important environmentally or biologically. So hopefully those will be things you're interested in. So stream water, the solvent would be the water, and all the other components would be solutes. Your blood's major component is water. So most solutions we talk about will be solutions where the solvent is water. So why do things dissolve? There are lots of reasons, but one is the energy change of the process. So if you have a solvent and a solute, so the top of this slide, and you mix them together, you're changing the interaction. So the long white lines are representing the intermolecular forces that hold two solvent molecules together. So if it does happen to be water, those would be hydrogen bonds. And if you're maybe dissolving sodium chloride, an ionic salt in that water, the solute-solute interactions or intermolecular forces would be ionic bonds. When you dissolve those two, you break those interactions, the solvent with itself and the solute with itself, and you create new intermolecular forces. So if it's an ionic compound in water, you create forces between the ion and then the dipole moment of the solvent, which is the dipole moment of water in this case. So when you think about it, when you have water and salt, in order for the two to mix, you have to separate all of the ionic bonds. So the last slide showed this in a different way, and then completely surround each of those ions with water molecules. And you see they're oriented in different ways. So if the purple ones are positive charged, the sodium, then the water molecules are going to orient their dipoles so that the negative part surrounds the positive ion. Be the opposite with the anion. So the chloride will be surrounded with water molecules where the orientation of them is such that the positive hydrogen end of the water molecules surrounds each of the anions. So when I need to let my cat out. Go ahead, you go out. About that. So when two things dissolve, something else changes, and that's the entropy. So when you start out and you have a pure solid and a pure liquid, the two red components on the left-hand side of the slide, and then you mix them together with two other, the ones in the middle, so liquid 1 and liquid 2, you go from pretty ordered systems to something that has less order. And you may remember from Chem 107, if it has less order, if things are more random, then we say it has higher entropy. So in general, when you make a solution out of pure components, the top row, a solid in a liquid, the second row, a liquid in a liquid, you are creating more entropy. So it has a positive entropy change for that process. And so we'll talk a lot more about a change in Gibbs free energy in one of the last chapters in this class, but at least in 107, you should have been introduced to the idea that it's really delta G, a change in Gibbs free energy, that will tell you if a process is spontaneous. So that combines both the delta H, the change in energy essentially, with the delta S, the change in entropy or the randomness. And you can either end up with positive or negative when you try to dissolve two things. So some things are soluble in each other and some things aren't. So if those components add up, when you add the temperature in there to give you a negative delta G, that process will be spontaneous. So whatever you're trying to mix will make a solution. If it's positive, then the opposite is true. Your solution won't form. Something won't dissolve when you look at those delta H's and delta S's that go with that process. We could just, oh, that wouldn't work. There aren't any. So one thing you should notice is that the delta S's tend to always be positive. There tends to always be more entropy when two things are mixed rather than when they're apart. The delta H depends on those intermolecular forces. So you see some negatives and some positives. To be able to measure that, you probably did a calorimetry lab in 107 where you measured a temperature change. So this is looking at, in the first case where I put calcium chloride in water, the temperature goes up, which means that process was exothermic, delta H was negative. There are other times ammonium nitrate, when you dissolve that in water, it's endothermic. So the temperature of the water goes down. So you can have either be true. It can be endothermic or exothermic when you dissolve something to make a solution. And the thing that determines that are those relative interactions. So it takes energy to break bonds or intermolecular forces, and you get energy back when they're formed. So you have to break the solvent-solvent interactions. So if it was water, you have to break hydrogen bonds. Then you have to break solute-solute interaction. So the example I used was sodium chloride. You have to break apart those ionic bonds. And then you get some energy back when the water molecules interact with the ions and you get new intermolecular forces. So depending on those relative quantities, you could get more energy back than you had to put in to break apart the interactions, or it could be the other way. You could get less energy back. And so this just shows that in a visual way where depending, so on the left-hand side, breaking the solvent-solvent is positive, the solute-solute is positive, but in this case, the green arrow is bigger than the sum of those two. So you get more energy back because the solute-solvent interactions give off more energy than it took to break apart the solvents and the solutes. And so the left-hand side shows you a case where it'd be exothermic. On the right-hand side, it's still true that the red arrow and the purple arrow go up. They have positive delta H's, but it turns out that the green arrow is smaller. So it takes more energy to break the solvent-solvent interactions and the solute-solute interactions than you get back when the solvent interacts with the solute. And so in that case, it would be an endothermic process of dissolving whatever you're dissolving in that case. And so we're going to talk about solutions. It's going to be important to have ways to talk about how much stuff is dissolved. So how much solute is present and how much solvent. So we're going to talk about concentration units. And for each of your tests, you'll get a note card. And I would highly recommend that you put these definitions on your note card. So molarity, moles of solute over liters of solution, and write that out so you don't misunderstand and think maybe it's moles of solute per liter of solvent. So make sure that you're very detailed in how you write these out. And so these are just different ways which will be appropriate depending on what kind of problem you're trying to solve, different ways to represent how concentrated a solution is. And so this just works through a quick example. If we have seawater, it's an aqueous solution of sodium chloride. And we want to know what its molarity is. So aqueous means that the solvent is water. So it tells us that the density of the seawater is 1.025 grams per milliliter when we're working at 20 degrees. And the sodium chloride concentration is 3.5 mass percent. So they want us to take mass percent units, let's go back, and convert it to molarity. It's not letting me go back. I don't know why. Let me go back here. Huh. Won't let me do that either. Interesting. I'll figure that out. So if we go back and look at mass percent would be how many grams of sodium chloride there are per total gram of solution. And molarity, remember, would be how many moles of sodium chloride there would be if I had a liter of solution. So this is really just a unit conversion problem. So if we start out and if we assume we have 100 grams of solution, then we can figure out how many liters that is. So we can use the density, take the 100 grams, multiply it by a milliliter would be 1.025 grams. So that first step cancels the grams. And then convert the milliliters to liters. With the conversion of a liter is 1,000 milliliters. And so this first calculation is taking the 100 gram solution into liters. And then we can convert the mass of the sodium chloride to moles. And you remember how to do that from 107 well, I'm sure. You look on the periodic table, get the mass of a sodium and a chloride added together, which is 58.4. So the 3.5 grams, if 1 mole is 58.4 grams, that quantity of sodium chloride is 0.0599 moles. And in both cases, we have the right number of sig figs. The first one is limited by the density with 4, and in the second one, we're limited by the molar mass, which has 3. Oh, okay, that's why somehow I wasn't, my screen was showing up. Okay, so now we want to calculate the molarity. We just take the moles divided by the liters. So that's pretty easy calculation. So you're saying there's 0.059 moles in 0.09756 liters. Therefore, if you divide the two, you'd have 0.614 moles in a liter of solution. This is a similar problem. We want to know what the molality is, which is a different concentration unit. If we make a solution by dissolving 0.385 grams of cholesterol in 40 grams of chloroform. So there's more chloroform than cholesterol, so the chloroform is the solvent. So if we want molality, we want moles of solute. Going back here, molality, the moles of solute over mass of solvent. So based on the relative quantities, the chloroform is the solvent and the cholesterol is the solute. So if we convert that mass of cholesterol to moles just by looking up the molar mass, which ends up being 386.0, we end up with 3 sig figs, so 0.000997 moles of cholesterol. The mass of the chloroform, we have 40 grams, is 0.0400 kilograms. So if we want the molality of the solution, we just divide those two. So this would give us units of moles of the solute over kilograms of solvent. So this is the table that has all those units in it. And so this is what I think would be really helpful to put on your note card. Just a little more discussion of solutions. What determines whether or not something is soluble? A solution containing the maximum amount of dissolved solute at equilibrium is called saturated. So when a solution is saturated, depending on what the combination is, it could be super concentrated or less concentrated. And so there are some important factors that impact when a solution is saturated, depending on the properties of the solute and the solvent. A supersaturated solution is a strange one. It's a solution that has more solute than it should have at equilibrium. And so this is a kinetic factor, which we'll talk a lot about the difference between kinetics and equilibrium. So this is a really good demo, and your book has a pretty picture, where on the left-hand side, you have, I think it's sodium acetate, in water. And you've heated it up and you've dissolved more than should be soluble at a lower temperature. And then you lower the temperature. But if you do that in a very gentle way, there's no crystal formation that starts. But it will start if you just give it a little incentive. So on the right-hand side, if you add just one crystal, the entire concentration of the sodium acetate almost will fall out, and you'll have this beautiful white crystal within a little bit of solution. So that's just an example of how you might make a supersaturated solution. This shows you that in general, when temperature increases, solubility increases of a solid in a liquid. So each of these are aqueous solutions of different ionic compounds. In general, glucose, which isn't ionic, it's molecular, but its concentration increases, sodium nitrate increases, sodium acetate, the green line increases. Some things are almost flat, like sodium chloride has the same solubility at all temperatures, so it doesn't depend on temperature. And a few things actually go down. So the cerium sulfate decreases solubility as the temperature increases. So temperature increases when you try to dissolve a solid into water. Another important kind of solution is a gas dissolved in a liquid. So something like oxygen dissolved in the water of a lake. In general, the concentration of the gas in the liquid decreases as you increase the temperature. More of that gas stays in the gas phase. So this is just showing that. And if you increase the pressure, makes sense, you're increasing the number of collisions with the gas molecules on the surface of that solution, so more will stay dissolved. So when pressure is increased, the solution's concentration goes up. So this is using that, So the equation for this is called Henry's law, that simply says the solubility is equal to K, which is Henry's law constant, times the pressure. So we have the solubility of CO2 in water. So that is usually an example of like a soda. When you put CO2 into a soda, then you have to keep that pressure above constant. So once you open the container, the CO2 concentration will go down, your soda will get flat. But in this case, if you keep it sealed and you have 1 atmosphere of CO2 above the water, then this is showing you that you'll have 3.2 times 10 to the minus 2 molar in CO2 in that water. So this is just asking you to calculate the Henry's law constant. So solubility equals Kp. So K is equal to the solubility over P. The solubility is 3.2 times. The pressure is given in atmospheres. So in these units, K would be 3.2 times 10 to the minus 2 moles per liters times atmosphere. So your Henry's law constant could have any concentration and any pressure unit, as long as you give it, so we know what you're talking about. And this shows what I said earlier, that as you increase the temperature, it's the opposite of a solid in a liquid. A gas usually becomes less soluble, has a greater desire just to stay in the gas phase than to be held in the liquid phase by the intermolecular forces. So the solubility tends to decrease with temperature if you're talking about a gas dissolved in a liquid. And that is it for what we're going to talk about in this chapter. Then we're going to move on to chapter 12, which is a chapter on kinetics. We'll come back to this idea of a solution and concentration units throughout the block. It's going to be super important. We're going to talk almost exclusively about reactions taking place in aqueous solutions. So I am going to end this first lecture and pick out some problems and do another lecture.